And welcome back to 101 Ways to Have Fun with a Whiteboard, Episode 3. Just how amazing is carbon anyway? Alright, so what we're going to talk about today is the fact that carbon can make millions of different types of compounds. More compounds than any other element on the periodic table. And this is because of a couple of things. It's because of carbon's size, it's a small size, but also its electronic configuration. So let's remember, carbon has atomic number of 6, which means it has 6 electrons in its neutral form. And remember, splitting up energy shells, we start off with the first shell, the 1s subshell. We have the second shell, which is made up of the 2s subshell and the 3p subshells, the 2p's. Okay, so let's fill up those subshells, starting from lowest energy level. Fill those up first, and that leaves us with 2 electrons in the p subshell. Okay, so to get stability, carbon wants to gain another 4 electrons, which is why it has a valency of 4. And it's the fact that it can form bonds to 4 different other elements, or indeed carbons or hydrogens, that we start to see that we can get a large range of chemical isomers, or indeed hydrocarbons, etc. All right, now let's have a look at methane, the simplest of the alkanes. Okay, so methane has 1 carbon bonded to 4 hydrogens. Now we know that these hydrogens are 109 degrees away from each other. That we know from our VSEPR model. The idea is that we want to minimise the repulsions between the electrons in those bonds. To get them as far away from each other we can, and the best arrangement to do that for 4 bonds is a tetrahedral arrangement where all the bond angles are approximately 109 degrees. The lengths of all these bonds and the strength are all the same in methane as well. And this is going to be important when we consider how we get from an individual electronic configuration from a carbon atom to actually working out the energy levels of the electrons in the covalent bonds themselves. Now, theoretical organic chemists first looked at methane and wondered, well, why couldn't we draw this structure? What's wrong with this? We have carbon with 8 electrons around it, satisfying the octet rule, meaning it has the nearest noble gas configuration. But instead of 4 hydrogen carbon bonds, we have 2 lone pairs of electrons. They theorised that why couldn't this exist as well? And in fact, later on it was found it can. It's a compound called carbene, but it's exceptionally high in energy. The reason why methane is lower in energy, and methane is a common chemical, although it's reactive, exists, basically comes from, let's have a look and see what is actually happening to the electrons in a covalent bond. Now, theoretical organic chemists theorised that because these bonds are all the same, really if we were just sort of overlapping 2s and 2p shells from 2 different atoms, we would indeed actually have 3 equal bonds of equal energy here, but we have 1 bond which would be higher in energy, and so it would have a different bond length, and methane would actually have an asymmetry to it. Now, we're familiar looking at a model of methane like this. It's symmetrical from every direction, and indeed we find that is to be the structure of methane. So we know that the electrons in all of these bonds have to have the same energy, and we're not going to achieve that by simply somehow overlapping these by themselves. So it was theorised perhaps what's happening is that we can hybridise these orbitals or make a combination of them. So the 1s we leave alone because that's not involved in bonding. Instead of writing 2s and 2p, I'm going to add these 2 shells together and create 4 new shells, and we're going to call those the sp orbitals. It's hybridized. It's a combination of s and p's. And of course, we put the electrons in them. 1, 2, 3, 4. And now, of course, we can start to make our chemical bonds. Okay, so what's happening? Let's have a look at ethane. Ethane, sorry. So remember, ethane, 2 carbons. Like such. Okay, so we need 3 of these bonds, okay, or 4 of these bonds for every carbon. Now when we add these together, remember the shapes of orbitals? So the S look like that, a sphere. The p orbitals, if you remember, are a dumbbell shape. And because of its asymmetry, as a node in the middle, there's 3 different ways of drawing those. We can have going horizontally, vertically, in and out of the board, which is why there's 3 different p shells. They just differ by their orientation. Add these 2 together, and we're now forming large lobe like that, and a small little piece at the end. And this is our sp3 hybrid orbital. Okay, and sorry, it's sp3, not sp, because we've added, we've added 1s to 3 p's to make up that orbital. All right, and there's 4 of them. So really, let's draw this instead of lines. Let's show orbitals, show what's happening. So each carbon in the middle. Let's draw the lobe here. The lobe here. I'm going to omit those little bits here. I can draw a lobe down here and a lobe here. Okay, and these are going to overlap with the 1s shell of hydrogen, because that's all that hydrogen has. And this is to form what we call a molecular orbital. And of course, the 2 carbon sp3 orbitals will also overlap. We can place our electrons in there, and place 2 in each bond, as we usually do when doing Lewis-Dot diagrams. And we can see that carbon has an octet around it. It is now stable, and each hydrogen has 2 around it. But indeed, what they're really in is in a new molecular orbital. So let's have a look at this bond here. So essentially what's happening is we have 1 carbon atom here, another carbon atom over here. We have our, I'm just going to draw the sp3 hybrid orbital, an sp3 hybrid orbital. They overlap and it creates a new molecular orbital, which is lower in energy. That's why it's more favourable to have this bond than not have it. So let's lower the energy. We form a new orbital, which is a bonding orbital, a single bond. We call this a sigma bond. There's also another one we can draw of higher energy, which we call an anti-sigma bond, but we're not going to talk about that. But essentially what's happening is 1 electron from each sp3, orbitals overlap, form a new sigma orbital, which is lower in energy. This is our bonding orbital, or sigma bond. Okay, our sigma bond here. Now the important thing about a sigma bond is let's have a look at a model of a alkane. And we notice that it's very easy in the model to rotate one of these groups around. And indeed that's what happens in reality as well. There's virtually free rotation about this single bond. Of course it needs a tiny amount of energy, but that can be supplied just through the medium that it's in. At very low temperatures this rotation may stop, but essentially because there's free rotation, when we rotate around the isomers, if we have this rotation, yes, it looks different from that rotation, but they're interchanging in solution all the time, and so they're not different isomers of each other. Okay, now, of course, we haven't just met alkanes, we've also started talking about alkenes. First of all, I'll show you this model. See if you can name that. I'm going to get you to press pause and have a go at naming that. Unpause. Okay, so we name the longest chain. We'll find the longest chain, which is 4 carbon atoms. They're the black ones. We find where the double bond is. Starts on number 2 We could say it starts on number 3, but if we rotate around, we can see it's the same thing, can't we? Okay, so this is butene. Now, the thing I want you to appreciate with the model is we have free rotation about this sigma, or